Hello and welcome to another episode of Sterling Seismic and Reservoir Services video series on reservoir analysis geophysics. Today's episode is titled Imaging Reservoir Fractures with DAS Seismic Data Using Diffraction Pre-Stack Depth Migration. I'm your host, Brian Fuller, VP of Reservoir Geoscience at Sterling Seismic and Reservoir Services. This presentation discusses the case in which there's a surface seismic source, as we have in this picture, and fractures near or even crossing a DAS fiber, particularly where the DAS fiber is in the horizontal part of the well, as we see in this picture. Seismologists have known for decades that faults generate diffractions when seismic waves pass them, and we routinely see diffraction energy on pre-migration stacks, so we know that this happens. So the question is, can even small fractures on the order of millimeters across generate diffractions? According to this 2019 book published by SEG, Numerical Modeling of Seismic Responses from Fractured Reservoirs by the Grit Characteristic Method, the answer to that question is yes. Even millimeter scale fractures should produce diffractions when a seismic wave passes the fracture. Additionally, easily observable phase reversals should occur that can tell us about the fracture width and orientation. There's just an example of one of the model results from the book showing some phase reversals for both P waves and S waves that are again related to the orientation of the wave field relative to the fracture, and additionally a function of its amplitude is also the width of the fracture. So we may have a pathway by which to learn a lot about fracture geometry and fracture properties based on diffraction behavior measured with DAS data. So can we actually observe diffractions using DAS data? The answer to that is also yes, as I'll demonstrate below. Just quickly, we use an acoustic finite difference modeling package with a simple constant velocity model to demonstrate the concept that we're talking about. So there's a surface seismic source at the top of the image on the right, and a DAS fiber, a horizontal DAS fiber at a depth of about 5,100 feet, and this tiny little 100-foot tall fracture above the DAS cable on the left-hand side. So a seismic wave propagates toward the fracture, and it keeps propagating, and then eventually the wavefront hits the fracture, and these basically circular wavefronts propagate out from the fracture. It's kind of like dropping a rock in a pond of water. See the wave field propagating out kind of like in a circular pattern. And the wave field here is, in our little model, is recorded on the DAS cable. Here's a picture of some model diffraction travel times that we would see on a horizontal DAS cable with a rock velocity of 13,000 feet per second. The vertical axis is time in milliseconds, and the horizontal axis shows data trace locations or data channels that were 13.2 feet apart on the DAS cable. The red curve shows event move out for a diffractor that's directly on the DAS cable, so the move out is linear. In other words, the wave field just propagates straight along the receiver cable, so the move out is linear. Excuse me. This curve is for a diffractor that's 100 feet below the DAS cable, and this one is for a diffractor that's 300 feet below the DAS cable. Diffractors on and below the DAS cable have this property that they are separable in time and in move out, as we can see here. Diffractors above the DAS cable, however, are more complicated. For example, this move out curve is for a diffractor 100 feet above the DAS cable, and this one is for a diffractor that's 300 feet above the DAS cable. Now, as we can see here, there is little differentiation for the diffraction events or diffractors above the DAS cable, at least at the near offsets. But at larger offsets, the different move out differences provide better differentiation. Now, the diffraction images that we show in some of the following slides were generated by summing energy along diffraction curves. The curves are based on interval velocity analysis. We won't show the interval velocity analysis here because it would add a lot of complexity and takes a lot of time, and it takes away from the primary message. Now we're going to show fracture images in a real time-lapse data set. So here's a sketch of the field setup. The well and the DAS cable are vertical to a depth of about 9,000 feet, and then the well turns horizontal for about 4,500 feet. We have 96 fiber-size surface shots spaced at a nominal 150 feet, and the sources extend about 5,000 feet off either end of the horizontal part of the cable. The baseline survey was recorded before the frac job for this well, and the second survey was recorded 4.5 months later. after flowback and initial production. So the next slide shows the P-wave fracture image prior to the frac job. This image is in depth, and the horizontal axis is data channel number along the DAS cable, and each channel is 13.2 feet apart in this case. So the DAS cable is shown here in red, and the total height of the image is 800 feet. The blue areas in the image are a lack of diffraction, to show a lack of diffraction energy, and the green and red show diffraction images, or diffractor images I should say, with red being the highest amplitude and green being somewhere between the blue and the red amplitudes. So again, this data was recorded before this well was fracked. The diffractors we see here must therefore either be naturally occurring fractures, or they could be fractures that were created when nearby wells were fracked. And we know that those fractures crossed this wellbore because we recorded those fractures as they passed by during a microseismic recording operation. So now we'll look at the diffraction map of 4+ months after this well was fracked. And remember, it was followed by that fracking was followed by flowback and production. The amplitudes between this image and the following one are comparable because this data set was processed for time-lapse analysis. So we did everything we could to homogenize time-lapse amplitudes and the waveforms. So here's the post-frac P-wave diffraction image. We can see that the completion and production process have resulted in more fractures. I'll flip back and forth here a couple of times so you can see the rather substantial change in these diffraction patterns before and after fracking. We can also look at the PS diffractions, and this is the image before the frac job, and this is the PS fracture image after the frac job. So again, 4+ months plus feed flowback and production. Again, we can see there was quite a substantial change between before and after fracking. How might a frac engineer use knowledge of fracture locations when planning pump schedules, or say perf cluster locations or plug locations? So the sketch shown here is a hypothetical toe-up geometry with fractures that we could image with this technology that we just discussed above. So right away we can see that 25% of the well at the heel, on the left end, has a lot fewer fractures than the remaining 75% of the well. So we could probably guess that the frac engineer would be more free with the pump schedule, knowing that the frac stage won't be pumping into a local pre-existing fracture. So we can guess they're going to have a little different way to frac than they will if there's a lot of fractures around. For example, contrast that with the stage between the two yellow plugs here, where there are obviously a whole bunch of fractures evident within the perf cluster. So we're going to probably frac that very differently than we will something at the far left end that has no fractures. And we can also see that the fracture density is greater below the well than above the well. So what does that say about the rock properties differences above and below the well, and will that fact affect the fracture parameters? Most frac engineers I know would say yes, it will. So all of the discussion above goes for the first frac job as well as it does for any refrac of the same well. We can also use this and some other related technology to map pressure drawdown zones in existing wells. If we're going to frac a child well next to the producing well, it's important to know about pressure sinks in the existing well. We know from microseismic and engineering studies, for example, that low pressure zones attract fractures from adjacent wells when the new well is fracked. So frac dollars that are spent fracturing zones that have already been produced are largely wasted frac dollars. Additionally, those reduced pore pressure zones on one side of the well actually reduce the fracture penetration on the other side of the new well, which further reduces the value of the frac effort. So knowing where pressure sinks are is useful in frac design work. If you have any questions about this or any other technology that's discussed on our Tech Talks webpage, please give us a call or send an email to one of the numbers or the addresses shown here. Thank you for your time, and thank you for watching.